I'm going to be talking about indefinite integrals. While taking derivatives of functions can in general tell us lots of useful information about it, sometimes we also want to be able to undo differentiation. That is, given some function, let's start with a simple example, f of x equals x. We want to find a function g such that g prime of x is equal to f of x. So a function whose derivative is the function that we already have, or a way to undo the differentiation. This particular case, let's start with something like x squared. We know that dx squared dx is equal to 2x. But since differentiating x squared with respect to x gives us 2x, we can simply divide by 2 to get something that differentiates to x. So dx squared over 2 dx is equal to 1/2 times 2x, which equals x. So the function we were looking for is g of x equals x squared over 2, right? But it's not entirely so simple. What if we had a function g of x equals x squared over 2 plus 7? Since differentiating g will get rid of the constant term of 7, the derivative of this function we can also write as g prime of x equals 1/2 times 2x plus 0, which is still x. So it turns out there can be multiple functions that differentiate to the same function. However, thankfully, the only functions that differentiate to some given function are ones that differ by a constant factor. So we can say in general that g of x equals x squared over 2 plus c for some constant c, and this will always differentiate to f, and nothing else will. Next, I'm going to introduce some notation. We say that the integral of f of x dx is equal to g of x plus c, some constant, if g prime of x equals f of x. So here, the first symbol I wrote is the integral sign, which denotes that this is an integral. The next thing is the function, and then dx means that it's done with respect to x, meaning that we're taking a sort of antiderivative of f with respect to x to get this g of x. Now it turns out that all of the rules that we've used for differentiation can be turned into similar rules for integration. For example, we know that dx to the n dx is equal to n times x to the n minus 1. So if we divide both sides of this equation by n, we get dx to the n over n dx is equal to x to the n minus 1, which we can now rewrite this new notation as integral of x to the n minus 1 dx is equal to x to the n over n. Or it's probably better to write the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 by replacing n with n plus 1. Similarly, just like we can interchange constant factors and addition with derivatives, we can do the same with indefinite integrals. So the integral of a f of x plus b g of x dx is equal to a times the integral of f of x dx plus b times the integral of g of x dx. And finally, we can take any differentiation relation we know and turn it into an integral one. For example, d dx of sine of x is equal to cosine of x. This is equivalent to saying integral of cosine x dx is equal to sine of x, plus c, of course. Although you can often ignore the constant factor as it's sort of assumed. And then similarly, we know that d dx of cosine x is equal to minus sine of x. Or we can rewrite this as minus d dx of cosine x equals sine of x. So this tells us that the integral of sine of x dx is equal to minus cosine of x plus c. We can continue in this fashion to evaluate all sorts of trigonometric integrals.